Section 7.7, we're going to learn how to write some slightly different types of equations for these precipitation reactions. And some of this applies also to other types of reactions. So what we've been looking at so far is what's called a molecular equation. The molecular equation shows the complete formulas for all of the reactants and all of the products. And if it's a solid, you just list it as a solid. If it's dissolved, you list it as aqueous. But everything's shown, and there's no charges visible. It's just all compound formulas. This is what people think of as a regular chemical equation. Then we have what's called a complete ionic equation. I can't draw a straight line today. That's closer. A complete ionic equation is going to show anything that's soluble as it actually is, dissolved into ions. So if you have potassium iodide, it's soluble. Instead of writing it together, you're going to show what's actually going on at this party, that the potassium and the iodide are not staying together, that they're separating and mingling around. So you separate aqueous ionic compounds into their constituent ions, but you don't separate solids, liquids, or gaseous compounds. So we need some examples. I guess we're going to talk some more first. What we'll find in that complete ionic equation is that we have some spectator ions. So if you go to a boxing match and you are a spectator, do you come out with a bloody nose and a black eye? Not unless things get really out of hand, right? But the guys down in the ring get all beat up, right? The spectators are really unaffected by that reaction that's going on. So a spectator ion is one that was in solution to start with, and at the end of it, it's still floating around in solution. So these are the guys that are, guys and girls who are still just unattached and available. Okay, they didn't, pair up with someone. So to simplify the equation, we often will not show the spectators because they really weren't part of the action. They just happened to be there, okay? And what we do when we eliminate those spectator ions is we get a net ionic equation. This is a little bit like your net paycheck, okay? This is where they've taken out the taxes and the Medicare and the FICA and all the other stuff that they take out. This is the bottom line. This is what you actually get to take home. The net ionic reaction just shows the compounds, the ions, that are actually undergoing a chemical reaction. Because those other ions, if we had different ions, it wouldn't matter. Okay, they were just there. So it shows only the species that actually participate in the reaction. So we use the word species a little different in chemistry than they do in biology. We mean a kind or sort of thing. Specifically, all the different molecules, atoms, and ions. It could be an ion, it could be a molecule, it could be an atom, different species. I'm so used to using that word, I can't use any other words. So here's an example. Consider this reaction. 2HBr plus CaOH2 reacts to form liquid water and CaBr2 that remains aqueous. This is not a precipitation reaction. There's no solid formed, right? This is some other type of reaction. We'll learn later this is an acid-base reaction. So we're asked to write a complete ionic equation and a net ionic equation for the reaction. To write the net ionic equation, you almost have to write the complete ionic equation first. If not on paper, then at least in the whiteboard in your brain. You have to be able to see it. So let's write the complete ionic equation. So in the ionic equation, what we're going to do is any ionic compounds that are soluble, we're going to write them as their individual ions. So HBr is aqueous. That means it dissolves into ions. Now you can pay attention to the coefficients to start with, or you can fix them up later. I prefer to just carry them along and just check them at the end. But if we have two HBr molecules, formula units, and those come apart, we're going to get two hydrogen ions and two bromide ions. I'm going to leave the state symbols out on these ions for now because there's not going to be enough room. I just know it. So that 2HBr is going to be, that's not going to work. We'll have two H pluses from that, and we're going to get two Br minuses from that, because those are the two ions that HBr makes. That's an acid, but when it's in water, it dissolves, it dissociates into ions. Then this calcium hydroxide, that's also aqueous. So we get Ca, 2 plus, and 2 hydroxide ions. Because in that equation, where am I? There I am. OH2. Each formula unit of CaOH2 has 2 hydroxide ions in it. And this is going to form liquid water. Water here is a liquid, so we're not going to try to break it into ions. We're just going to copy it down. 2H2O. I'm going to put liquid there just to remind myself. And then this last compound is also a soluble ionic compound, aqueous. So basically, if its state is aqueous, pull it apart into ions. Otherwise, just copy it down. So calcium bromide is Ca 2 plus 2 Br minus. See how I did that?
Is there a trick to distinguish capital O's from zeros? Like, because that looks like 20H negative, but like, is there like a trick you use to differentiate?
That's a good
The
question.
two?
Oh, you put a line through it? With the angle line, 0?
I've never had anybody ask me that before.
Oh yeah.
That's a good
Well,
question,
that's what I
though.
was
It looked
thinking.
like
We draw a
20.
line diagonally through it to
Zero,
make it
zero.
Yeah, I make my Z's with a bar so they don't look like 2s. And 7s have a line so they don't look like sloppy 9s. So, sometimes a 0 is done like that. And so if you're confusing yourself, do that. On a multiple choice exam, the capital O is going to be round, and the 0 is going to be skinnier.
Okay.
So when it's typewritten, it's easier to see. Most of these equations are going to have smaller coefficients, and so we're not going to see things as big as 10 and 20.
Okay.
But that's a really good question. So now what we need to do, that's our our total ionic equation is showing all the ions. Now technically you should put AQ after each of those ions, but I knew there wasn't going to be enough space. Now what we're going to do is we're going to look and see what was just a spectator. What didn't get involved in this chemical reaction, this chemical romance, okay? Well, bromide. There's 2 bromide ions on the left and 2 on the right. Nothing happened to bromide. So I'm going to cross that one out. And the calcium. Calcium didn't find the right girl that night. Okay? So did it really matter if they were there or not? No, it didn't. Nothing happened to them. They didn't get changed. And so for the net ionic, we're just going to write down the things that something happened to. So we cross off the spectators, and then we just copy down what we've got left. So we've got 2H plus, and now I've got a little more space. I'm going to put these in, plus AQ, plus 2OH minus AQ. And that's going to form 2H2O liquid. Now what could we do to that equation to make it better? Is that the lowest ratio of coefficients? No, it's all 2s. So we could get rid of those 2s. Essentially we're dividing the whole thing by 2. Just get rid of those 2s. Because it's 1 hydrogen ion and one hydroxide ion get together to make one water molecule. It is true that two hydrogen ions and two hydroxide ions would make two water molecules. But we're going for simplest. Yes, question?
Oh, is that an L in the parentheses next to H2O?
Yes,
That stands for?
liquid.
You wanna put AQ for the fact that it is also soluble itself.
Well, water can't dissolve in itself.
It was part of itself.
It is part of itself,
We have to-
but it's a liquid.
Okay.
Yes, it's a liquid. And L's, 1's, and capital I's are easily mixed up. And so I write my L's as a script L. And I write a 1 is like this, and a capital I has bars on it, just to distinguish them.
Does solubility, I wonder, refer to like changes in the liquid form, or could this same change happen in like the air and like gas? Yeah, like hydrogen gas.
Well, all gases are soluble in all gases. So we really don't have any, that's a weird property of gases. The solubility really only happens when you have things in a liquid.
Okay.
And you can have liquids being soluble in liquids, or solids being soluble in liquids, or gases dissolved in liquids.
What about ionized states for plasma?
We're not going to talk about plasmas.
Like,
It's beyond the scope of this class.